And let me see, go here. And okay. Now I can solve different problems because we're just gonna do different ones. I will do one because I know that that people have some difficulties on how to, so practically. In the problems that we do, there are ways of doing things in a simple way, and there are ways, to simplify things, and there are ways to do the same thing accurately, but in a very complex way. And I think we need to learn how to use the most simplistic way to get what we need to get. So I will solve a problem which shows you in how many different ways you can avoid doing very long calculations with some things. And then I will look at some other problems, or I will solve problems. If you tell me where you find difficulties, I will solve problems related to those difficulties. And then, so we'll do things from there. So here is the one thing that I wanted to solve for you. Let's assume that we have two vectors, A and B. And I'm giving you these two vectors in what system? Let's assume that I'm giving you in a difficult thing, the two vectors in a spherical coordinate system. Okay, so just to make it difficult, or cylindrical. Let me give it them to use cylindrical one, not make it that complex. So let's assume so that I give you these vectors. So A, let me find two examples of vectors in the cylindrical system. One case. I'll find from here. Okay. So vector. Okay, so here is the vector. One vector is given like this. A sub rho cosine phi plus A sub phi sine phi plus z, A sub z rather. Okay, and then let me give you another one. B equals A sub bar plus A sub phi cosine phi plus sine phi A sub z. Okay, I just made them up, to tell you the truth. They don't mean anything. It's just a mathematics. And let's assume now that I'm asking you to do the following. To find A dot B, okay? I would like you to find A cross B, and then I would like you to find A plus B and A minus B. Okay, we'll start one at a time, all right? Let's see. The A dot B is rather simple. What does that mean? We do the rho with the rho components, phi with the phi, z with z. All right, so A, we'll start with the simplest one. So A, so find here. So that's problem 1. All right, so solution. A dot B. How are we gonna do that? We'll take the row component of 1 and then find the product with the row component of the other. So practically it's gonna be row cosine phi plus the phi component of 1 with the phi component of the other. It's going to be sine phi cosine phi. And then the z component of 1 with the z of the other, plus sine phi. Okay, that's A dot B. A cross B. All right, how do I find A cross B? I go to the formulas that I gave you. Remember those? How do you do the cross? Let me also go here for a book from where I took these formulas and I gave them to you. So, in fact, at the end. Here, I don't have those in front of me. Yeah. 3. Let me find them. Where is, give me the notes, but I don't find them here. 1 second. Let me find the A cross B. There. Okay. So the A cross B in cylindrical will be rho phi. I mean A sub rho. Let me be consistent how I write them. A sub rho, A sub phi, A sub z. Then we'll have the first one, the row coefficient of the first, which is going to be rho cosine phi. Let me move this out a little bit. All right. A sub phi, which is sine phi. And then A sub z, which is 1. And then I have the other one. The row component of B, which is 1. The phi component of B, which is cosine phi. And the z component, which is sine phi. And that gives me A sub rho. And then I have sine square phi minus cosine phi plus A sub phi with a negative which is rho cosine phi sine phi. And then I have minus 1 plus A sub z. And then is rho cosine square phi minus sine phi. Okay, that is like an implementation of the inner and the dot, I meant to say, or inner product, the dot product and the cross product in cylindrical coordinates. Okay. Now, I'm asking you, let's assume now that I'm going to find A plus B. How am I going to do that? So can I just go here and sum them one, like I do in the X, Y, and Z? I cannot do that. You know why? In the X, Y, and Z, all of the components X, Y, and Z are along the same direction. All right, so all of the X components is along the X-axis, all of the Y components along the Y-axis, and all of the Z components along the Z-axis. But when I go into a cylindrical system, which looks like this, all right, the coordinate system has the R direction, the phi direction, and the Z direction. The only thing, so every point has a different A sub bar and a different A sub phi. If I am here, this is my A sub bar, this is my A sub phi. This is the tangential. If I'm here, this is my A sub bar, here, this is my A sub phi. So again, I cannot sum them like this. All right, I cannot just sum them like I would do with a Z. The Z remains the same for every point, but everything else changes. So I cannot do it there unless I transfer, unless I do crazy things in terms of transferring to X, Y, and Z possibly, or something else. So what I will do is I scrap this. I keep that in mind, but I'm going to just get rid of it for a moment and say, all right, what else do I know that may make it easy for me to go A plus B or A minus B? Okay. Do I know the magnitude of A and B? Yes. How much is the magnitude of A? The magnitude of A is how much? Square root of A sub rho squared plus A sub phi squared plus A sub Z squared. And I have given you this, all right? And the magnitude of B equals what? B sub rho squared plus B sub phi squared plus B sub Z squared. So I know them, even if it's a function of phi, but I know them. I know what they are. For every phi, I can find them. For every rho, I can find them. Okay. So if I go and use these formulas, then magnitude, right, make them small for a second so I can see them. So magnitude of A will be square root of rho squared cosine square phi plus sine square phi plus 1. Okay? From the formula. Okay. Then how much is B? Same way. Is 1 plus cosine square phi plus sine square phi. And in that case, just happened the way I gave it, this one is going to be square root of 2. So the magnitude, while the vector the same has components that depend on phi, each of them components, the magnitude is just happens the way I gave it to be square root of 2. Okay? Now, what do I know about A dot B? What do I know about that? Do I not know that if I have two vectors, A and B, and this is theta? Do I not know that this is equal to A, B, cosine theta? What do you think? You know that. So now practically I know cosine theta, which is this one. And I can say theta AB, just so we know what we are talking about. Okay, let's assume for a moment that instead of phi, I will give you a given phi just to make things simpler. All right, but I can do what for any phi. I can do this thing for any phi I'm talking about, but I can make it simpler for you. Do you want me to give you a given phi, or you want me to continue with these expressions? You can speak out. Can you hear me?
Yeah, that's fine.
Okay, that's fine to continue like that, or to give you to simplify it.
It's fine.
Like this.
Yes.
What is okay? Perfect. So let's try to find the vector, the angle between the two vectors. Since if I know the two vectors and if I know the angle, I know a lot of things after that. And what do I know after this? Do you remember from the previous homework? Then if I know the two vectors, I can find the sum and I can find the difference. Do you agree?
Yes.
How is this? Yeah, how do I find the sum here? I bring the one vector here. All right, I transfer A to this point, and then what is the sum? Okay, what is the difference? Who will tell me?
The tail of A to the, tail of B.
Yes, exactly. So practically, I move this here, but I change the direction, and it's going to be from here. So it's going to be, if it's A minus B, did I say, or B minus A? I said A minus B, A minus B. So I'll bring, so to find the correct direction for this one, I have to be careful. I will move B to the end of A, but I will change its direction. So for B, I will go like this. I will translate B, make a translation, but I will change its direction. Okay, so practically A minus B will be this one. So practically is this one. All right, A plus B is the purple, A minus B is the green. So if I were to remove for a moment these two, I did them all to find the correct direction of B. So the green is A minus B, and the purple is A plus B. What do these two remind you? What do they remind you? Who's gonna tell me?
Parallelogram?
Yes. So if I call the green Q, which is A minus B, and if I call the purple P, What do we know about this parallelogram? We know that P squared is going to be A squared plus B squared plus 2A B cosine theta, AB. This is from the parallelogram. Okay, and then Q is going to be what? Do you recognize those formulas? We use them in the homework. Can you? So it's going to be A squared plus B squared minus 2A B cosine theta AB. What is P? P is A plus B, isn't it? What is Q? Q is A minus B. Do I know everything here to find this? Yes, because I know this from the inner product, from the dot product, or inner, that's how we call it also. That's why sometimes I call it inner product. This is the dot product. And I know this. So now I found P and Q, A plus B and A minus B. See how I do it? Simpler. If I were, to tell you the truth, to do this by all of this, and because I wrote, I mean, it's like 1 page maximum. If you write it a little more, because now I wrote big things, but it's a 1 page solution. Do you know how many pages would take you to try to take the A and B vectors into a coordinate system and put them in X, Y, and Z and then sum them up and then take the difference? I don't know how many, lots of pages, and possibly with mistakes, because they're very tedious calculations to get there. So that's one way of solving the plus and the sum and the difference of vectors. If you have 2 vectors, you find the dot product, you find the cross product, because these are the easiest to find in any coordinate system, and then the sum and the difference from this process. Any questions about that?
Yes, ma'am. You said we couldn't take the addition directly because at different points of the cylinder, we would have like different radius around.
Yes.
Or what was your explanation?
You cannot sum them up directly because, as I said previously, at every point, the direction, the radial and the phi direction change. So you will have, if you were to do it accurately, you will have to take everything into the X, Y, and Z coordinate system where all X are the same in parallel, all the Y, it does not matter how many vectors you have, all of their X components are along the same direction, all of their Y components are along the same direction, and the Z, so you can sum them up. But if you go to cylindrical or if you go to spherical, that's not true. And gets very intense computationally. This is the best way to find the sum and the difference.
Okay, thank you.
Sure. Any questions? Okay. Tell me, do you have a preference of what kind of problems to solve? I could not hear you. Could you say it again?
Can you go over something similar to quiz number 2?
Yes. I think I put the solutions up.
Is there another example that you can do with us? I just want more practice to look over that type of problem.
Okay, similar like where I ask about
A
rotational
solenoid.
or solenoid. Yes, okay.
Yes.
We can
Thank you.
do that. Sure. So let me find it. And sometimes I give problems myself and they're complex. So let me find something from this book to solve. A solution at the end. Okay, wait a moment. Let me find the right. Well, okay, I'm gonna give you one on my own. Let me see. I got another book. This is not our. I found whatever I found in my office. And okay, let me just give you one. I'll make one. Okay, that's problem 2. Okay, consider a field or 2 vector fields or a vector field, a field, right? Okay, vector field rather. A vector field E of X. I will try different coordinate systems, Y and Z, where E has X E naught plus Y, and then it's E naught of X plus Z, which is, there's something there, strange, but X, it's, okay, wait a second. E naught, this is E naught, but I will put an EX, and then EY, and EZ, okay. I don't know who is going to make that field, but let's assume that there is a vector field like this. All right, and then I say, find out the characteristics, identify, classify this field. Classification means 2 things. Answer the question, is this field a solenoid? That's question number 1. Question number 2, is this field a rotational? All right, is that the one you were suggesting? Okay. Solenoid, how do we define a solenoid? A field is a solenoid when a field is a solenoid when you remember? The divergence of this field is what? All right, do you remember that? Yes?
Yes.
All right,
Yes.
let's try then to answer the first question. Is it a solenoid? Is that 0? So in the Cartesian coordinate system, the divergence of V is what? Theta, well, let me put this on x, a sub x, a sub x, a sub x, a sub y, a sub z. When sometimes you see me doing that, because I have the tendency to do it for simplicity, is the same like a sub x, all right? A sub y, a sub z, it has the hat, so it's a unit vector. But the book uses alpha sub x, alpha sub y, alpha sub z, so I have to do what the book wants. Sometimes I forget. Okay, so this is theta, theta x, theta, theta y, theta, theta z. And then we have here ex, ey, ez, the three components of the vector field. And that gives a sub x, theta ez of theta y minus theta ey of theta z plus minus rather a sub y, and then it's theta ez of theta x minus theta ex of theta z plus a sub z theta ey over theta x minus theta ex over theta y. Okay, what I have given e sub x is constant. All right, so I will call this e sub x 0, just to make sure. This is a function of x, this is a function of y. So the way I've written them, maybe, you know, so let me do this so you don't get confused. I'll put here a function f of x, and I will put here another function, because this e sub y and e sub z confuses you, g. Okay, is that better? And this is a constant, ex naught. So ex naught is e sub x. F of x is e sub y, and g of xy is e sub z. So then what I write here is that the divergence of E is E sub z, let me write it here, A sub x, and then I have E sub z is g, theta g of x and y over theta y minus theta of f of x over theta z minus a sub y theta g y over theta x minus theta z of v x naught, which is a constant, plus a sub z, which is theta f of x, theta x minus theta ex naught over theta y. Okay, so now let's see what happens here. The zeros. This is a 0 because ex naught is a constant. This is another 0 because this of the same reason. This is a 0 because it's a function of x and we take the derivative of z. And everything else is not a 0. All right. And since I have not given the functions, you assume, that obviously there are going to be some derivatives, obviously, because there are functions of x and y. There are going to be they're going to have both x and y. If it's a function of x, only x. So the derivative of each one of those will exist. So practically that tells me here what I found, that this is not 0. So as a result, this is not a solenoid. Okay, not a solenoid. Sorry. Look at what I've done. Why did you guys not correct me? What did I do here?
You're supposed to just do dot product because you just did the cross product, right?
Yes, I did the cross
I was very
product.
confused for like
You
10
have to
minutes.
stop me. Yes. I saw that and I said, oh my God, what the heck am I doing? So that's not a solenoid. This is not rotational. Not rotation. Well, excuse me. This is rotational because I would have failed that class from day one. Because this one is not 0, therefore this is rotational. Okay, I did the most difficult one first.
I have a question.
Yes.
So to be rotational, you only care about the cross product. It doesn't matter what the dot product is equal to. Okay.
No, that is gonna no, because you can be a solenoid and you can be rotational.
Okay.
So
okay.
how is a solenoid that is rotational? Think like think of a snake. I don't know if you hate snakes. Or don't think of a snake, but think of a hose, of a water hose. All right. A water hose, assume that there is a water hose like the water without the hose. Assume that you could somehow sustain this water and then consider the water hose going like that. The water in a water hose that is has this like a spiral, it's a solenoid, but is rotational. It's one thing to be a solenoid and it's another thing to be rotational. You can be rotational and not being a solenoid where, I go like that. So it does not go all together and rotate, but it goes one like this and the other goes straight. One part of the field makes a rotation and the other goes straight. That can be just rotational. All
Okay.
right. So
Okay.
they're
Thank
two
you.
separate properties. They can coexist or not.
Professor, sorry, I had kind of like the same question. I just want to clarify. So you find the cross product and that alone determines like rotational or not. And then you find the dot product and that alone like determines solenoid or not solenoid. Like you don't need to use both of them in conjunction to find like whether it's rotational or not. Because I think
No.
like notes, it's like in some of the notes it would be like two properties and then it would say like solenoid. So that's why I was getting confused.
Yeah, if you look at the book also, because sometimes I write things, but also you need to, so my notes are only supplementary. You need to also look at the book. Yes, each one of them can stand separately. You can be a solenoid and be rotational. You can be a solenoid and not be rotational. You can be rotational and not be a solenoid, and you can be both. And they're independent. They can coexist rather.
Okay.
They can coexist and it depends on the field.
Mm-hmm.
Okay. And also remember something else. This is what is happening at one point in space. What happens later might be a different story. Now, of course, I gave you a formula. See what it is. I gave you a formula that, assumingly, this particular formula applies in the whole domain. But a lot of times, I may give you a form for the field that applies in a subdomain. All right, might not necessarily be that a field can have this form for every x, y, and z. It could have this form for a subset of x, y, and z. In that then subset, in that volume, in that subdomain, it will have whatever properties, you know, the cross, the curl, and the dot give you. So the curl here, which is not 0, tells you that it is rotational, meaning it turns, all right? It makes rotations, not perfect rotations, but it will turn in places. Let's see whether it's a solenoid though, as this happens. Solenoid, which is A, it has to be the dot. And that is theta x ex plus theta y ay plus theta z ez. And that will give 0 to the first one because this is a constant up there. Okay, so it's going to give 0. This is a 0. E sub y, but it's a function with y. All right, see the E sub y, this one is theta f of x theta y, which is also 0. 0. And what is this one? This is a derivative of g of x and y theta z. How much is that? 0. So what happens to this field? It's a solenoid. Okay. I can give you something like that in the other coordinate systems. Let's see. Do you want me to do that for practice? Or you're good with that? You want to go to something different?
Yeah, we can do one more.
One more. Okay.
Yeah.
How about if I give you something in the spherical coordinate system? Okay. So problem 3. Okay. Now, assume that you have a vector field. Consider a vector field A to B. Let me see whether I will find something here. I had seen something. Okay, I found something. Let's assume that I have a vector field that is A 2 R plus R or 1 over R. Let me just do that. Or R rather. R cosine phi okay. I said spherical. All right, so I'm gonna classify this field. So practically I have to find this and that, but in spherical coordinates. Okay. So practically we need to find, and then we, on the basis of what we find from each one of those, we'll classify. All right. Let's now take again, because I don't remember by heart like everybody else. We don't remember by heart how the divergence is easy, but we don't remember the curl. Let me find the table. Okay. Let's start with the divergence. In spherical coordinates, the divergence is the simplest one because practically it's theta. Here. Spherical. Okay. It's not the simplest, but it is in some ways. All right. In spherical coordinates, and this was, okay. You have to find out how the divergence is because it's the following. It's not easy. It's 1 over r squared theta r squared a sub r plus 1 over r sine theta and this one they brings the theta first, that's okay. And then a theta, let me make it smaller. A theta sine theta and then plus 1 over r sine theta d theta a phi theta phi. Okay. So a sub r is 2. So let's look at that. This is going to be 1 over r squared theta r 2 r squared plus this is 5. So it's going to be 1 over r sine theta. And then we have r, well, let me rewrite it, theta phi of r cosine phi. And then plus this one, the theta piece, 1 over r sine theta partial with respect to theta. The alpha a sub theta is 1, so sine theta.
Professor, in the
Yes.
second term, what happened to the sine theta that was next to a theta? Like it's
This one, no, this one.
yeah, because you in the second line you put like 1 over r sine theta and then sorry, not theta, phi. You put like r cosine phi, but in the previous line it's a theta sine theta. I'm just confused about the second term.
Okay, let me just do the following.
She swapped them.
Yes, I will remove this here.
Oh, okay. I'm sorry.
That's okay. It's all right. Yeah. Okay. So obviously, this is not zero. This specifically, the first one is going to give 1 over r squared. And then it's 4r times 4r. And then here plus 1 over r sine theta. And then we have another r here in the sine theta. And then the derivative of the cosine, which is, how much is the derivative of the cosine?
It's a negative sign, right?
E to the j phi plus e to the minus j phi over 2 theta theta phi, which is j e to the phi minus j phi minus j phi 2. Yes, that goes down, becomes negative. And exactly what you said, e to the j phi minus e to the minus j phi over 2j, which is sine. Oops. Which is minus sine. All right, you remember that? Okay, just as a tiny note. So obviously this one is going to give a minus sine phi. And how about this? How much is the derivative of sine theta for the same reason? How much?
Is that cosine?
Yes, cosine theta. So what we get from here, which is interesting, from the divergence of A, is 4 over r minus sine phi over sine theta plus 1 over r sine theta, and then here cosine theta. So obviously, what is interesting from this is that for some values of theta and phi, it is possible that that can go to 0, but not for every theta and phi. All right. So in general, yes.
What page of the book is the equation for the dot product for spherical coordinates on?
So in our book, I don't have our book, but okay, 1 second. If you can, 1 moment. Let me go to 1 second, if you can. Try to go to Howdy to see the notes that I've given you. Maybe not, it's easier, I have them on my computer. 1 second. I want to see what I have incorporated in what I gave you. 1 second. Wait. So I have not included this in my notes, so it should be in the book. If you go in the book, I don't have the book with me here, but I can, at the same time, I can take a picture of these from this book and then upload them. Because it's very nicely done. And this book is on the back page. So it's easy for me to take a copy. But it should be in the book. It's just, I don't know whether, and maybe look at the back of the book, because usually every book has those put together. But I can make a copy and then upload them as well.
I think you did upload it on the 29th of January lecture notes.
Yes, but they did not incorporate that one. It did not have, it had the cross and dot product, but it did not have the differential operators. So I will upload them. I'll take a picture of this and I will upload it. It's gonna be easy, but the book should have it. And just check the book at the back or the front. Usually they have them separately, you know, like either in appendix form, because I remember I saw them in the book somewhere at the end. Just check the end of the book. I don't expect anybody, even myself, I don't remember. I mean, no, I remember that it's something complex, but beyond that, I don't remember. I have to copy it from somewhere. So that, of course, in general, for it in the whole volume, maybe in places, maybe in points, in some points, it might be that at that point, it does not seem like it may be like at that point may look like a solenoid, but in general, this is not a solenoid as a field in the whole space defined for that field. Okay. Now you can do the same for in the spherical coordinates. Usually tends to be the most complex is in the spherical coordinates because the cross product is even more complex. And I can write the cross product for you, but I will not do it. But it's a very complex thing. So for example, and I did it so, not because I want to give you something totally crazy, but to show you that even the process, if you follow the process carefully, you can really apply that in any coordinate system. So for example, let's do the curl. Why not? We have time. The curl here is a sub r 1 over r sine theta, and then it has theta of that partial derivative meaning, and a sub 5, this component, sine theta, minus the partial derivative of the theta component with respect to phi. That's one. Then a sub phi is 1 over r, a partial derivative with respect to r of r a sub theta minus partial derivative of a sub r with respect to theta. And then the last is the theta component, 1 over r, and then 1 over sine theta, theta, partial, meaning derivative with respect to phi of a sub r minus partial derivative with respect to r of r a sub phi. Okay, Now, let's see what we have. A, let's write it here. A sub r equals to A sub phi equals, what did we say? R cosine phi. And A sub theta equals 1. Let's see what goes to 0. Okay, this goes to 0. This goes to 0. This goes to 0. This goes to 0. Okay, so then, in fact, that does not, let me see, A sub r, no, all of the A sub r's go to 0. Theta, that one does not go to 0. You know why? Because it's a derivative with r, but it adds an r in there, so that does not go to 0. So A sub phi, no, go to 0. A sub r theta, A sub r phi, that goes to 0. So now what we have is the following. Then we have equal A sub r 1 over r sine theta. A sub phi is r cosine phi, so I will
Excuse me, Professor?
Professor, we can't hear you.
Professor, I think you have yourself muted.
Okay,
I can hear you
drop me
now.
off the system. Wait a second, I'll tell you what happened. It dropped me off the system, the Zoom. So I have to connect again. Can you hear me now?
Yes.
Yeah. So for some reason it dropped me off. Let me try to reconnect. 1 second. Okay. You know, Zoom at this time of the day is very unstable. It's not very good. One moment. Okay. Okay. Whole process to get. Okay. Okay. All right, I'm here again. Wait. Can you hear me? Can you hear me now?
Yes.
Yes.
Okay.
Yeah.
All right,
Yes.
thank you. Apologize for all of this. Okay. So screen this one. I was asking the question. Was somebody asking a question when I got disconnected? My notes get disconnected.
I don't think so.
Okay. Now, so to remind you, this is the process. You just go through it carefully, make sure that you are using the right formulas in the right coordinate systems, and that's all right. And then just do carefully the differentiations. Now, I have to tell you that the fields I gave you here are kind of crazy. I don't know who is generating those fields, but I did them. I did not give you something simple so you can see how you even work it out when it's kind of complex. But obviously, in our case, the fields that we will see are not going to be crazy like that. It's going to be a lot easier to identify whether something is a solenoid and or rotational. What kind of other problems would you like me to solve?
Can we go through something like the exercise 2 on the top hat?
Could you remind me what I asked in exercise 2?
So basically, it's just like, I think it converts the vector from one coordinate system to another.
Okay, sure. Yes. Let us try to, I'm getting now in front of the table that I believe similar to it I have given you. Just a second, let me get. Sure, okay, let's do that. In fact, what was I asking you there to do? Could you tell me exactly? I know that you're asking me to help you go from one coordinate system to another, but what was the problem there, to just change coordinate systems?
Yeah, so basically you give us a vector in cylindrical coordinate system, and then you ask us to the question is, what are the components of this vector on the x equal to 0?
Got it. Okay. Let's do that. So problem 1, 2, 3. All right, so let's see. Here I might have a problem like that, so I don't make it up. Make something crazy. Let's see. Okay, it says here problem. Transform, it gives vectors, transform the following vectors into cylindrical coordinates, and then evaluate them and the indicated points. Good. So it says here, so consider the vectors. A equals A sub x plus y. Then B equal A sub x y minus x plus A sub y x minus y. And then I'll give you another one. And then there is a C, which is A sub r cosine phi plus A sub phi sine square theta plus A sub theta sine phi. They're vectors. And then say transform these vectors to the cylindrical coordinate system and evaluate them, give something interesting and evaluate them at points as I write them next to them here in the cylindrical system. P1, 1, 2, 3 in the cylindrical system. And then P2, 1, 0, 2. Oops. And P, so So PA rather, yeah, P1, P2, P3. And 3 pi over 2. Okay, no, these are, let me see. These are not, sorry, the way now I realize it's not in the cylindrical. It gives you the points at the Cartesian systems. System, Cartesian. So practically, what it is asking us to do is to take each one of these three, move them to the cylindrical coordinates, but then try to see how they will look in the cylindrical coordinate systems at these points, which are at the original. All right, see this Cartesian, Cartesian, and this is in the spherical. That's what the problem says. Okay. Now, if you take the formulation that I believe I have given you, or they are in the book, it says the following: how to change a transformation from Cartesian to cylindrical. All right, so practically, the vector, how do you do the vector components? Here, let's take A solution. Let's take A. A has two components. We can write it like this. Where A sub x equals x, A sub y equals y. Now, in the cylindrical system, A would have this form. All right, let me use a different color so we don't get confused. In the cylindrical system, A will have this form. A sub rho plus A sub phi plus A sub z, z. Okay, and then according to the book or the formula that I believe I have given you, but is also in the book, what you find is A sub rho is nothing else but A sub x cosine phi plus A sub y sine phi. And this is equal to x cosine phi plus y sine phi. So that's A sub r, A sub rho rather. A sub phi. And in fact, so you, just to make it easier, here is going to be A sub x. Okay. A sub phi equals minus A sub x sine phi plus A sub y cosine phi. And also in what we have, that A sub z is equal to any A sub z if there was in the Cartesian system. We don't have A sub z there. So what we have from here is that A sub z is 0, obviously. We have A sub rho equals x cosine phi plus y sine phi. And we have A sub phi equals minus x sine phi plus y cosine phi. And then you can put them back here. And that gives you A in the cylindrical equal x cosine phi plus, plus y sine phi, A sub rho, plus minus x sine phi plus y cosine phi. And that's, I need to transfer it. A sub phi plus 0. So that's what it is in the Cartesian system. Now what is asking us to find is where, what is the value of this vector at point 1, 2, 3 of the Cartesian system. So at point P 1, 2, 3, what does that become? 1 is x, y is 2, and z is 3 in the point. But A only has x and y. So A, which means is independent of z. All right, so for every z is the same. So A at that point, at point P, will be cosine phi plus 2 sine phi A sub rho plus minus sine phi plus 2 cosine phi A sub phi. So practically now, what you've done for all of this is to take the vector A and transform it into cylindrical coordinates, and also be able for any to find the value of that for any point in the Cartesian system, but you still have it in cylindrical coordinate form. So that's how you transform a vector to another system. You can do the same thing for B, and then for C, you have to move from spherical to cylindrical. Okay. So I'm not gonna do the second one, it's the same, all right? This one is like the same as we did before. So you can practice that one. But let's do C. So what do we have? That C, vector C has one component A sub r, and we need two A sub phi, A sub theta. So in the cylindrical coordinate system, it's gonna be 0, C, I meant not Z, C rho, A sub rho, plus C, C sub phi, A sub phi, C, Z, A, Z. Okay, now C sub rho will be C sub r from the spherical sine theta plus C theta cosine theta. C sub phi is going to be A sub phi, C. The C sub phi is going to remain the same thing with before. Is C sub phi same between the two systems? And then you have CZ. That's why it was good to use a different color rather. So we know what it is. Okay. And C sub Z will be C sub R cosine theta minus C sub theta sine theta. Okay. Let's see, take this down here, copy this. All right. Okay, so C sub R is this one. Let's C sub R without, wait. C sub R is this one. This is C sub phi. This is C sub theta. So if I go above there, above, I'm finding the following. C sub rho will be cosine phi sine theta. C sub theta is plus sine phi cosine theta. All right, and C sub phi is sine square theta, and C sub z is cosine phi cosine theta minus sine. I've left something here. Sine. Cos sine phi sine theta. Okay, so that's what you get. Do you know how much is the first one? How much is this? Can you recognize that?
Is that 0?
Why?
Oh, I'm not sure.
You
Just-
remember the sine? Oops. Let's write that. Sine theta plus phi, how much is it? Sine theta cosine phi plus cosine theta sine phi. All right? Remember that? This formula? And cosine theta plus phi is cosine theta cosine phi, I believe is minus theta sine phi. But let me figure it out. Okay, sine, wait a second. Just make sure that I'm correct. Sine A plus There we go. Everything is available. All the formulas are available nowadays. And I am correct in both of those. So I remembered well the sign I was wondering about. So practically, this one is sine theta plus phi. This one is what it is. This one is cosine theta plus phi. This is how it simplifies. And now is asking us, all right, now it's asking us to find this vector at what point? At this point. Copy. Here. Paste. So we need to find this C, vector C at point P3. So practically, I will substitute in there. And we have, it's going to be A sub rho, C of rho will be theta. Here, let me tell you according to that, it's going to be R, this is the original vector. It was R. This is phi, and this is theta. Okay, so now let's see what it is. A sub bar sub rho here is sine of the sum of the two, which is 3 pi over 2. How much is 3 pi over 2 over sine? Is it not
One.
minus 1? Yes?
Is it 1?
Minus 1. Cosine is 1 is here. Sine 1 is at pi over 2 is 1 here. This is 3 pi over 2 and it's minus 1. Sine are here. You remember that? Cosine is there. So 3 pi over 2 is minus 1. Okay? This is minus 1. And, well, of course, that's the only one component, but let's look at the other one. So let me put here this one. Okay, so let me do this here and put this is minus 1. And then I will add the other components. Plus A sub phi theta pi. How much is sine of theta of pi? 0. So times 0. And A sub z cosine of this 2.3 pi over 2. So cosine of 3 pi over 2 is also 0. So 0 here, 0 there. So practically, vector C at point P3 is minus 1 times A sub rho, or minus A sub rho. So we don't confuse ourselves. We think it's something else. Minus A sub rho. Okay? That's how you solve these problems. Always use the book or look at the formulas to make sure that you use the right ones. But, you know, that's how you do the conversions. Any questions? Anything else you would like me to, what else you would like me to solve? Or do you have any particular questions then? Something more specific. You know, we are not going to do this weird stuff later, as you can see, as we go down this class. This is just games. It's like you play a game to get comfortable. We are not going to see these kinds of things. But what I would like to pay your attention to is, yes, you would like to solve a few problems. So when you solve a few problems like this, you know, this technique here is to help you avoid unnecessary calculations. And you would do unnecessary calculations if you would compute A dot B, A cross B, and then you will go to change this into a Cartesian coordinate system and then sum them up. There's no need, because you can do it here much faster, because you saw what it takes to transfer coordinates from one system to another. That's why you always keep that in mind, all right? Problem number one. Problem number two is how you classify the fields, whether it's a solenoid or whether it's rotational. That is useful in many ways, even if the fields that we will have will be a lot simpler. It's useful to recognize at least the electric and magnetic field in very specific arrangements, like if you in a capacitor, in a parallel plate capacitor or in a cylindrical capacitor. I mean, these are important ways to visualize the fields and to be able to help yourself in this process, because visualizing in engineering, we are not mathematicians. Visualizing what we are trying to develop is extremely important, unless even when you write a code, you need to have, even then, but you need to have some kind of the ability to understand the structure. But in circuits, in antennas, when you design things like that, visualization in three-dimensional spaces is extremely important, because it's like you lay out circuits. If you cannot visualize a circuit on how it's gonna be laid out, how is it gonna look in 3 dimensions, how is it going to impact the whole thing? Yes, there is software and everything, but your ability to also do that is gonna be very useful as a designer. So understanding the space, being able to visualize it is important, all right? So understanding whether the field is solenoid is important, because if the field is in a solenoid form, it does not spill over to other places. If a field is rotational and solenoid, it's okay, you don't worry, because it may do turns and stuff, but it's not gonna spill over, like it's not gonna diffuse out of the pathway, if you like. But a field which is not solenoid and has rotations, it goes all over the place. And in some cases, this is very important to understand it. So that is important to be able to know how to classify fields and to practice a little bit with transformations of one coordinate system to another, just when you have to do it. Because if we don't practice at all, even if we are not going to do this kind of complex things, if you don't practice at all, you're not going to even be able to do the simple things. So that is what my advice will be. Any other questions you may have for me? I will publish these notes, and the recording for those who have approached me that had a conflict, a serious conflict, they could not come together. If you know, however, other people who want to ask, for those of you who participated, who want to ask you some questions, please feel free to explain to them or to help them. No problem with me. Any questions? Anything else? What else? How else? What else do you want me to do to work on today? Or you want me to? Well, what else you would like me to do for next time? Maybe I can do something to help you with the homework for next time, depending on where we are going to go. So I will see what we have learned by next Monday, and then I will prepare something. Okay?
Yeah, that sounds good.
Okay.
Yeah.
I hope those sessions will help, in some ways. We'll do the best we can to help. And then, of course, some days, so my advice is try to solve your homework now. At least you will have one way of solving one problem in a simple way. And then Sunday we will have office hours, and then you can ask me if there are any other questions you may have.
Professor, is that possible that you can release more practice problems without grade that stuff, just like practice?
Do you want me to just give you practice problems or solve practice problems?
I mean maybe problems with answer. So that's I can know the approach to do that.
Well, okay. So here, let me just tell you that I can only recommend out of books.
Oh, sure. Yeah, definitely.
All right, I can do that because I have to tell you, it takes me a long time to put the material for the class in place.
Oh, sorry. Yes.
And that will make it very difficult, all right, to do plus that as well. But what I can do is, first of all, I would say the book has a lot of examples. So, and the solved examples. So I would start with that first, but I can, find if I can look at some other books and then put some other, I have a book, but it's the problem is that I'm a little cautious about getting problems from other books because we don't necessarily cover everything, all right? Every lecture, we cover the fundamentals, but sometimes a problem that might be easy for another book because there was a solution in that might be very difficult for us. So I would suggest that you start, here's my advice, start with the examples of the book. That's why I selected this book because of the many, many, many examples. Some of them are very hard, as a matter of fact, but they are solved. All right, they're the solved examples. That's what I mean. Start with those, and if you need more than that, then come back and tell me, and I will provide you with something. Obviously, yes, but I don't want to give you something from another book that might be easy, and then we get twisted trying to solve it.
It's just I'm good for now, but it's in the beginning of class, especially for the coordinate conversion, that part is sometimes confusing. And
well, you know what it is in the beginning of this class is always tough. You know why? Because there is material that we've had long time ago. Yeah, we're not going to cover in detail, but we have to review quickly, and then it is always starts hard. Let me tell you, because of that, because we have to go back and look at things that we've done some time ago, but we don't remember it for a good reason or other. Because if you don't see this material for a long time, who would remember it?
Yeah.
But as it goes down, it's going to get, because we're going to do over and over the same thing. We're not going to see every time new stuff, you know. We're not going to get that. More of the same, rather.
Yeah. Thank you so much.
Sure, no problem.
All right, thank you, Professor.
You're welcome. Thank you.
Thank you, Professor.
Okay, no problem. Thank you.
Bye, Professor. Thank you.
Take care.
Thank you.
Bye-bye.